The previous two lessons we talked about indefinite integrals, and that's where you find the antiderivative in the family of functions. Now we are going to talk about the definite integral, where the process of evaluating the integral is very similar, but it has an extra step. Instead of finding a family of functions, we are going to find an actual numerical value. And there are two ways to look at this. Let's first look at the meaning of a definite integral in terms of the graph. So we have our function here in red, and here's the x-axis. And let's say we want to find the area under the function and over the x-axis, so between the function and the x-axis. Now we don't have a geometric formula for this shape. We have formulas for circles and squares and triangles, but not for that shape. So we're going to have to be creative. So what we can do is we can take the interval from 1 to 4 and break it up into subintervals. So in this case, we have 3 subintervals. We have 1 to 2, 2 to 3, and then 3 to 4. And for each of those subintervals, we're going to set up a rectangle so that the width of that subinterval is the width of the rectangle, and that the height of the rectangle is going to be the value of the function. So these 3 points here will represent the 3 heights for those rectangles. Now we can then add up the area of those rectangles because we know how to find the area of a rectangle. So we find the area of each one, add it up, and that will give us an approximation of the area that's under the curve and over the x-axis. However, we have this space here. This space that's white was not counted in the area of the rectangles. So when we add those 3 rectangles together, those areas, we're going to have an underestimate because we didn't include these spaces. So if we want to make it more accurate, we can create more rectangles and more subintervals. So let's say I want to go and have, let's say, 10 rectangles. Now you can see that the area that's in white that wouldn't be counted with the area of the rectangles has gotten smaller. So going from 3 rectangles to 10 rectangles made the area that we're estimating more accurate. Now let's try 40 intervals with 40 rectangles. Now you can see that there's almost no error. There's very little space missing between the rectangle and the function. So the more rectangles we create with subintervals, then the more accurate that area is going to be. So now when we apply this process to the definite integral, what I want you to imagine is from 1 to 4, we are making infinite number of slices. So we're just going to make so many slices, you can't even count it. And so when you are evaluating a definite integral, that's what you're doing. You're adding up the sum of all those slices on the interval that you're trying to find that area. So when you do that, you'll find the exact area because we have infinitely many slices versus estimating with rectangles. So now looking at the second meaning of the definite integral, if we think about applications, when we come up with a value, we want to interpret what that means. So when you evaluate an integral over a specific interval, you are going to be evaluating the definite integral. But in this case, when we're talking about it in an application where we want to interpret what that value means, that is going to be the total accumulation of the unit over that interval. So for example, if we have the marginal cost function, that's going to be a rate. It's going to be a rate that tells us the cost per item. So now if we find the antiderivative and work backwards, the marginal cost, when we integrate that, will give us the cost function itself. But then when you additionally evaluate that over the interval from 0 to 100, because X represents the number of items produced, that value, when we integrate, is going to tell us the total accumulation in cost from 0 to 100. So in other words, the total cost of producing the first 100 items. So now that we have an idea of what we're doing as far as graphically and what the value would mean when we actually find that value, we're going to look at the fundamental theorem of calculus. Now, there are two parts to the fundamental theorem of calculus. We're going to only cover one part, and the part that we're going to cover is explaining how the definite integral is defined. So if we have a function and we're looking at it from the interval from x equals a to x equals b, normally, just like what we do when we have an indefinite integral, we find the antiderivative. So we're going to call that capital F. So this is the antiderivative. And then what we would do is we would plug in the values of a and b and find the difference. The order matters with this. It's very important that you start with b. So you plug in b into the antiderivative, and then you subtract the value of the antiderivative at a. One thing that I want to point out is notice with the definite integrals, we don't have a plus c here. And I'm going to get into that on the first example, why we don't need it. And then one last thing is more vocabulary. When you're looking at the interval from a to b, this value here down, this value here a, that's called the lower limit of integration. And then this b here would be called the upper limit of integration. So let's look at our first example so that we can see the fundamental theorem of calculus in action. So let's say we want to find the value of the integral from 3 to 5 of the function x squared plus 3x minus 2. Now, we're going to approach this the same way that we did in the previous two sections. We're going to work backwards to find the antiderivative. So I'm going to add one value to the 2 and then divide by that same value. So we're going to have x to the third divided by 3. When we work on this term, we're going to add the exponent, add 1 to the exponent, and then divide by that. So I'm going to add 1 to the exponent and get 2, and then we have to divide by 2. That's going to give me this. And then when I find the antiderivative of this minus 2, that's going to give us minus 2x. Now, in our first example, I'm going to purposely put this constant in so that I can show you why we don't necessarily need to put it in future examples, but I wanted to walk you through with our arbitrary constant so that you can see how this works. Okay, so here's our antiderivative, and we want to evaluate that from our lower limit of 3 to our upper limit of 5. So the way that we do this is we literally just plug 5 into our antiderivative. So I would put 5 in for all these x's. So I would have 5 to the third over 3 plus 3 times 5 to the third over 2 minus 2 times 5 and then our plus c. Then we're going to subtract what we get when we evaluate this antiderivative at 3. Now be careful when you subtract the second part for when you're evaluating the lower limit, because this subtraction is going to apply to every single term. We're applying it to the entire antiderivative. So remember to either distribute this minus and make sure you switch all the signs right away, or put parentheses around it to make sure that you don't forget to distribute it. So what's going to happen is these values here, the first, second, and third term of the antiderivative evaluated at 5, and the first, second, and third term when we evaluate the antiderivative at x equals 3, we just use order of operations to determine that value. But when we're looking at our c's, notice we have a plus c. This is our arbitrary constant, and then we subtract a plus c. So really we're doing c minus c. So the c's, when you are doing a definite, excuse me, when you're doing a definite integral, the c's are going to cancel out every time because you're going to evaluate it twice and subtract. So every time these are going to cancel and add to 0. So this is why you don't have to worry about the constants when you are doing or evaluating an definite integral. So all we would have to do is find all of these terms, evaluated, and then combine them using order of operations. And when we do that, we would get 158 over 3. Okay, now that we've gone through a really basic definite integral, we're going to step it up a little bit, and we are going to evaluate a definite integral where we have to use substitution as well. So when I look at this integral and I use substitution, I would want to let x minus 3 be equal to u. So that's what we're going to have over here. And then when I find the derivative of u, that's going to give us just 1 dx. So I can directly substitute in du for dx. So when we do that, we get 1 over u because this was u, and then the dx becomes du. Now, what's different here that you can't forget to do this, because these upper and lower limits of integration is with respect to x when we're looking at the first part of the question. When we replace it with u's, we need to make sure that we adjust those limits of integration to reflect that it's in terms of u. So what you want to use is however you set up your substitution, you want to use that to figure out what the values of x are in terms of u. So notice that our lower limit here is 4. So when x is 4, I plug 4 in here, and I do 4 minus 3, and that gives me that u is 1. So now, instead of having 4 as the lower limit, we're going to replace it with 1. So 1 is our new lower limit. Now we have to replace 10 so that it's in terms of u. So if I plug 10 in here, I'm going to get 10 minus 3, which is 7. So when x is 10, u is going to be 7. So now this is our new upper limit, that's 7. So now we're going to go ahead and evaluate. When we find the antiderivative of 1 over u, we know that that's the natural log of the absolute value of u. And we want to evaluate that from 1 to 7. So first we're going to plug in 7. And at this point, since you know we're using positive numbers plugging in here, you don't need to put the absolute values. You can remove them. So we're going to find the natural log of 7, and then we're going to evaluate it at the lower limit. So we're going to subtract the natural log of 1. Now the natural log of 1 is equal to 0. So we're just going to be left with the natural log of 7. And again, like I said, you can remove the absolute value since we know that what we're plugging in is a positive number. So when you are using substitution, with definite integrals, it's really important to make sure that you change your limits of integration as well. Okay, in example 3, we're going to evaluate the integral from 0 to 1 of 3 times e to the 3x dx. Now, one of my hints before in the previous lesson, I told you when you're doing substitution and you have an exponential function that you want to try first to let u be whatever that exponent is. So that's what we're going to start off with. That typically works. So I'm going to let u be equal to 3x. So when I take the derivative of u, I'm just going to get 3 dx. So this e will now be raised to the power of u, and I would still need to replace the 3 dx. And what we have is that 3 dx is equal to du. So the 3 in the dx is now going to be replaced with du. So now we have e to the u of du. But we have to change our limits of integration. Looking at the lower limit first, this is our equation that we're going to use. When x is 0, u is going to be 0 as well. So the lower limit is not going to change. It's still going to be 0. When we're looking at the upper limit, when it's in terms of x, we want to plug in 1 for x, and we get that u is 3 times 1, which is 3. So the upper limit is going to change when it's in terms of u. It's going to go from 1 to 3. So here are the new limits of integration. And now from here, we're just going to find the antiderivative and then evaluate. So the antiderivative of e to the u is just e to the u. And we're going to evaluate that from 0 to 3. We're going to always start with the upper limit. So when I plug 3 in for u right here, I'm going to get e to the third. And then I subtract what I get when I plug in for the lower limit. So I subtract e to the 0 for plugging 0 in for this u here. Now e to the 0 is equal to 1. So what we're going to end up with is e to the third minus 1. This is what's called the exact value. If you turn it into a decimal and approximate it and say we're going to round it to the nearest hundredth or thousandth, that is an approximation, but you can certainly do that. Just pay attention to the directions to make sure that you're following either the rounding directions or you're making sure that you're putting in the exact value. So in example 4, we're going to integrate from 0 to 1, 6x plus 1 times e to the 3x squared plus x. This looks really, really messy. So we're definitely going to have to use the substitution method. And again, one of my hints was that if you're dealing with an exponential function, usually if you let u be the whatever the exponent is, it usually works out pretty nicely. So we're going to start by trying u is equal to the exponent, which is 3x squared plus x. When we take the derivative of u, we're going to get 6x plus 1. And of course, we have to make sure that we have this dx here. So notice that's exactly what we need to replace. So this 6x plus 1 and this dx is going to get replaced with the du. This 3x squared plus x is going to be replaced with the u. So we end up getting e to the u du when it's in terms of u. But now we have to make sure that we change our limits of integration to reflect the fact that we're doing this in terms of u. So we need to figure out what the values of x equals 0 and x equals 1 is compared to the values of u. So when we look at 0 first, if I plug 0 in for x squared here times 3, and I plug in 0 for this x, I'm going to get that u is also 0. So the lower limit is not going to change. However, when I plug in 1 for x to check my upper limit, if I plug 1 in here and 1 in here, that's going to give me 3 plus 1, which is 4. So I need to replace that upper limit with 4. So now when we actually go through and evaluate this, we know that the antiderivative of u, or sorry, e to the u, is e to the u. So we need to plug in 4 first. That gives us e to the 4 minus, then we got to plug in 0. So that gives me e to the 0. And that gives me e to the 4th minus 1 because e to the 0 is 1. And I want to stress how important this is to make sure that you always do the upper limit first. The order matters here. Looking at example 5, I'm going to evaluate the integral of 4 over x times log, or natural log of x squared, and then dx. This is what we want to evaluate. So looking at this, it looks fairly complicated to do it directly, so we're definitely going to have to use substitution. But before we start looking at the substitutions, my preference is to make sure that all of my exponents, or all of my terms that has exponents, are pulled up into the numerator, because then we can use the power rule. So I took this natural log of x squared and brought it up as a -2 exponent. I left the x here because I knew from experience that this was going to be more useful in the denominator. However, if you don't catch that right away, it's a quick, easy fix. If you actually bring that x up, when you find your substitution, you're going to see that it's easier to put it in the denominator, and it's just a quick fix to do that. So, if you recall, in my previous lesson, one of the hints I gave you when using substitution was if you see a composition function, if you have an inner function of some sort, typically letting u be equal to that inner function works pretty well. So here's my inner function. Instead of having x to the -2, we have an entire function plugged in there. So I'm going to let u be my inner function. So I have u is equal to the natural log of x. Then I find the derivative of u, which would be 1 over x dx. And this is why I let x stay in the denominator. From experience, I knew that we were going to get 1 over x. And so I can take 1 over x dx and replace that with du. So this x in the denominator and this dx is going to get replaced with du. This 4 is just a factor that we can carry along. So this 4 remains here. Now I have u to the -2, and then the x in the denominator and the dx is replaced with du. Now we have to find our new limits of integration because we did a u substitution. We can no longer keep those limits of integration in terms of x. So I'm going to look at the lower limit first. When x is 2, I plug in 2 here, and u will be the natural log of 2. So this is our new lower limit. Remember, this is just a value. It's written in a way that is a little bit unusual that we're not used to yet, but this is literally just a value. It's some number. Now, let's do the same thing with 4. 4 was our upper limit when it's in terms of x. So when I plug 4 in here, I get that the upper limit in terms of u will be the natural log of 4. So I changed my upper and lower limits, so I have the natural log of 2 and the natural log of 4. Now that we have our integral set up, now we're going to find the antiderivative. And so we want to add 1 to the exponent and then divide by that same exponent. So we're going to have 4 times u to the -1, because when I add 1 to -2, that gives me a -1. And then I have to divide by -1. And then I'm going to evaluate that from the natural log of 2 to the natural log of 4, keeping in mind that it's really important to start with the natural log of 4 because that's the upper limit. So when I take the natural log and plug that in for u, I can actually flip it down. This -1 means in the denominator, it's u to the positive 1. And we can't forget this negative here. So we have -4. And then when I plug in natural log of 4 for this u, because it's a negative exponent, that gets flipped down into the denominator. Now you don't have to do that. It's my personal preference not to have negative exponents. Now when we subtract the antiderivative evaluated at natural log of 2, we're going to get a double negative. We're going to subtract a -4u to the -1. So this negative in the subtraction when we evaluate becomes a positive. And then when we plug in the natural log of 2 for our u, we get 4 over the natural log of 2. If we approximate that with the decimal, we get 2.885, and that's going out to the thousandth place. However, just again, watch the instructions and make sure that if it asks for the exact value that you're putting in this first part here. And if it says we want to approximate it to a certain number of decimal places, then you put in the decimal value. In our last example, we're going to walk through an interpretation of this. Now, this I actually used as an example at the beginning of the lesson where we were talking about the two different meanings of the definite integral. So I'm going to walk you through this to kind of refresh you on that idea. And then we'll talk about it in terms of profit or revenue. So the question says, if C prime of x represents the rate at which the cost of producing x items changes as the number of items produced increases from A to B. We're going to interpret the meaning of this definite integral. Now, although we don't have specific values plugged in here, we can still interpret it. So this prime, if you recall, lets us know that we're looking at the derivative of the cost function. So that's why it's talking about the rate at which the cost of producing X items changes. So this is the rate, this is the derivative. So when we find the antiderivative, that's going to give us the actual cost function. And then when we evaluate it from A to B, that specifically means it's going to give us the total cost of producing the number of items from A to B. So for example, if I'm just going to make up a number here, let's say we got out $2,000 for our integral. That was our final answer. And the limits of integration was, say, 100 to 200. So what this means would be the total cost of producing from 100 to 200 items, that would cost a total of $1,000. Now, this same interpretation can be applied to profit and revenue. If you have the profit function with the prime, so we have the derivative of the profit function, and we set it up the same way, it's just going to give us the total profit of producing and selling from A to B items, whatever that interval is. And then the same thing applies to the revenue as well. If we find the antiderivative of the derivative of the revenue or the marginal revenue over a certain interval, that would mean the total revenue of producing and selling from A to B items. So from, say, 100 to 200 items, when you sell and make from 100 to 200 items, it would give you that total revenue.